Hello everyone. In this macro video, I will talk uh, or to explain how to use MATLAB to solve a differential equation in order to obtain the time response of a system or a differential equation. For example, I will solve the uh, differential equation I gave for in the example of second lecture. As you hear, we have the equation of motion as my double dot plus by dot plus ky equal to ut, which ut is the step input. Let's assume that ut is equal to 0 in order to, without loss of generality, just to explain how to solve this differential equation. So in MATLAB, I need to open up a new editor page. I use the command clc, clear all, close all, and then I need to define a for loop in order to solve this differential equation. But before that, I define my variables. M equal to 100 kilogram and K 10,000 Newton per meter and B 750. I here define M equal to 100, B equal to 750, and K equal to 10,000. Since I'm using for loop, I need to define counter variable. For example, let's see I equal to 0. Since my differential equation is in terms of time, I need to define my loop in terms of time. For example, for t from 0 with increment of 0, 1, or before that one, let's define dt equal to 0.01, since I need to use dt several places. So here dt, and let's say up to 10 seconds. To solve the differential equation, we have different methods to solve them. The simplest method is the finite difference method. Using the finite difference method to see how the finite difference method works, we need to know the definition of the differential of a signal or variable. For example, x dot t has been defined as limit of xt minus 1, which is the time. T is the current time, and t minus 1 is one step behind the current time, over delta t, which is the time difference when delta t goes to 0. If we ignore the limit here, we can estimate xt as x dot t multiplied to delta t plus xt minus 1. So this is the simplest way to estimate the variable xt based on this derivative. There are other approach, more accurate and precise approach, such as ODE45. I recommend students to see how ODE45 works. To check that one, you can use the help ODE45. Here you can see the detailed instruction how to use ODE45. Students also can use the command doc ODE45, which MATLAB opens up is a help window and gives a detailed instruction about ODE45 and other differential solvers. So, but in this example, I used just a simple finite difference. If you look at the equation of motion, I have my double dot plus by dot plus ky. In order to use the finite difference, I need to define the initial condition for the y and y dot. So before here, I put, for example, y equal to 0, y dot equal to 0. But since I have some I have free vibration or free motion, I need to have some initial condition. So let's define y equal to 0.5 as the initial condition and y dot equal to 0. So y double dot is equal to my double dot. If you look at here, the equation of motion that we have, I have is my double dot plus by dot. So we need to fix this one. Okay, plus y double dot plus by dot plus ky equal to 0. So it means y double dot is equal to minus b over m y dot plus k minus k over m y. So if I use this here and y dot will be equal to y dot t will be equal to y double dot t multiply to delta t plus y dot t minus 1. So I can calculate the velocity of y, and then I can calculate the position as y t equal to y dot t times delta t plus y t minus 1. So so if I use the same methodology, I will have first I equal to I plus 1 semicolon y w dot equal to minus b over m multiply to y dot minus k over m multiply to y semicolon. So because I want to plot a y dot and the y as a response to the system, I need to save it as a vector. So I use it y dot I equal to y w dot multiply to, if you look at here, I have defined dt delta t as 0.01. So dt plus y dot, or let's say first define the y dot here as this one. If you look at here, we have a y dot in both sides. In fact, the y dot is the previous value of y dot, and the y dot in the left side is the new variable. So this one is the y dot t minus 1 in fact. And I calculate the y equal to y dot multiply to dt plus y. But I need to save this y dot and y in the variable as a vector in order to have the time history of these variables. So I put the y dot I equal to y dot semicolon and y capital Y equal to y semicolon, in fact y I equal to y, and I need to save my time vector as well, which would be t semicolon, and then I use the command plot in order to have the y dot and y in different figures. I use the command figure 1, then I use a command grid in order to grid the window, plot t and y dot, and then I use command, then I create another figure window, figure 2, I call it figure 2, grid plot t and y. I need to save it. I save it as an example, and then run this command. As you see, I have two figures. Figure 1 is the velocity of response, and figure 2 is the displacement of the response. As you see, initial condition for the velocity is 0, so it has to the initial condition for the displacement is 0.5. That's why the position starts at 0.5. You can't change the dimension of the scale of the response. For example, 10 is too much. I reduce this to 5 or even less, let's say 3. Here is a better shape of the response. As you see, it's starting at 0.5, oscillating and reaching to the steady state value, which is 0. And for the for the velocity, again, if I change it to, for example, 3, we have the velocity response, but it has to be grid. I don't know why it's not gridded. If I use the command grid here, so let's see, yeah, it has been gridded. So this is the response of the system. This is a simple example to show you how to use to solve the differential equations using the finite difference method. But what I recommend you, strongly recommend you learn how to use OD45, which is much stronger solver for the solving differential equations. If you have any question, please feel free to come to me or ask me during your tutorial session. Have a good night.